Now we've seen that the altitudes of an equilateral triangle meet at a point which divides the altitudes in the ratio 1 to 2. That point is an orthocentre. And now we're going to show that the orthocentre of a tetrahedron divides its altitudes in the ratio 1 to 3. Now here's a model with the altitudes shown, both the altitude of the equilateral triangle, which is the face, two of those, and also two of the altitudes of the tetrahedron, which is, of course, are an axis of rotation as well, running down here. So we want to show that that length there is 1, whereas this length is 3. If that is 1 unit, then this is 3 units. And we're going to use similarity to prove this. If we look at this model, we can see that we've got an angle here in this triangle. That triangle, there's my right angle, it goes to that point, and there's the bottom of the triangle. So we do have a right angled triangle there, which turns out to be similar to the right angled triangle that you can see in here. Just about, that's better. So if you can see this triangle, there it is, there's our right angle, and here's the other side, the hypotenuse running down there. Now those two triangles are similar, and so we can use ratios in order to investigate how the orthocentre divides the altitude. Let's look at a diagram. Now we've got BC here, that would be BC at that point. This is the point A. This is the point, making sure you can see this, this is the point D. And the orthocentre itself is, that's it, is there, which is the point E on this diagram. These triangles must be similar because they have a common angle, and they've got, both have a right angle, so the other angle must be the same as well. Now looking at this, we can see a kite. We might just be able to see the kite here actually if we look at it from the right angle. Yes, you can see there's one side of the kite, there's the other side of the kite, and the two other sides which are equal are the bottom quarters of the altitudes. So we know quite a lot. We know, for instance, that BC and DC must be the same. And we know that DC is 1/3 of AC, the whole of that length there. Because that's the face of an equilateral triangle, that's the altitude of an equilateral triangle. We also know that EB is equal to ED, because those are what we hope will be the bottom quarters of the altitudes of the tetrahedron. Well now, if we set out the letters carefully, we can see that in this triangle ADE, A is the common point, then D is the right angle, and E is the other one. For the other triangle, we've got A, B is the right angle, and C is the other one. So now we can use those letters to fit together some algebra. Now what we want to show is that EB over AE is equal to 1/3. Well, first of all, EB over AE is the same as ED over AE. Now, ED over AE is the same as BC over AC by similarity. But we know something about BC. We know that BC is equal to 1/3 of AC. So let's write it like this. That's 1/3 times AC, which is what BC is, and then we're going to divide it by AC times 1 over AC. Now that can be divided out, numerator and denominator, so we're going to be left with just what we wanted. EB over AE is equal to 1 over 3, which tells us that the ratio is EB to AE in letters and 1 to 3 in numbers. So that's proved what we wish to prove at the beginning, that the orthocentre of a tetrahedron divides the altitudes in the ratio 1 to 3. There's one further step now showing that the triangle in our net has the ratio root 6, 4, and the next video will show why that must be the case.